Okay, so we shall look at work and look at some of the energy transformations connected to work. So we saw last time that the energy in a system could be written, so it could be written as E mechanical. So the total energy of the system will be the mechanical energy, or let's say the system's energy, E system. This would be equal to the kinetic energy plus potential energy, and then we can also include some thermal energy if we want. So this is the total energy of a system. If the energy of the system changes, we can write, so change in energy of the system, E system, like that, and that will be given by change in kinetic energy plus change in potential energy plus any changes in thermal energy of the system. And that should be equal to work done by the system, where we say W is equal to work done by system. And so we can get a convention for work. So we can say that if the work is greater than 0, if W is greater than 0, then we can say the environment does work on the system and system's energy increases. We can say the energy of the system increases. On the other hand, we can say that if W is less than 0, then the system does work on the environment and the system's energy decreases. Okay, so that's the convention we shall use. And then we can say that, so we can also say that if the work done is equal to 0, then any change in the energy of the system is equal to 0. Therefore, energy is conserved. Okay, so we say that if the change in energy of the system is equal to 0, then it will mean that change in kinetic energy plus change in potential energy plus any thermal energy should be equal to 0. Or on the other hand, we can also say that, or we can say that E final minus E initial is equal to 0. Therefore, E final is equal to E initial, which is the same as saying that energy is conserved. So let's look next at work. This is work and kinetic energy. We looked last time at work and elastic potential energy. So today we're looking at work and kinetic energy in this section. Let's consider an object of mass m moving, let's say from a point or a position xi to x final, where its speed changes from v initial to v final. The motion is caused by a force F. So we can say, for example, that the object is moving along this path. So this will be, say, v initial, a certain force F acts on it, and it ends up at this position with a velocity v final. Okay, this is at an angle theta, of course. Well, let's leave the angle out for now. I think we shall do that at a different point. We can leave the angle out for now. Let me erase that so that I can take the angle out. So it's the same, everything is the same. We have the force F and the force F, so this is V final. Okay, so we can find the relationship between work and kinetic energy. So this object has a mass m and it's moving from one point to the other. So we can say that the net force on the system F is equal to mass times acceleration. So the net force is equal to m dv dt, which we can write as F equals m dv dx times dx dt. Okay, so we will recognize that dx dt is v. So we can say that F is equal to m dv dx times v. So you can write F equals m times v dv dx, like that. And then we shall just rewrite it as m times v mv dv equals f dx, and then integrate both sides from v initial to v final mv dv, and then you are integrating from x initial to x final f dx. So this becomes mv squared over 2 v initial v final equals f times x initial x final. Okay, this is for a force, a constant force. Okay, assuming the force is constant. If F is not constant, then we can leave it the way it is. We'll just say that mv squared over 2 v initial v final is equal to the integral of x initial to x final of f dx. So we'll just leave it that way. We'll come to the calculation later on when we want to find f, or when we want to find work. So what this tells us is that, so we know that mv squared final over 2 minus mv initial squared over 2 is the change in kinetic energy, and work is equal to integral from x initial to x final f dx. So this just tells us that the change in kinetic energy is equal to work. So this is our work energy theorem. We've used it a little bit in the past, but we didn't explicitly state it. So this is the work energy theorem. The work has the unit of joules, where 1 joule is equal to 1 Newton meters. Okay, that's our unit. So the work energy theorem has an analogy to the impulse momentum theorem. So let's create an analogy. So we know that the impulse J was written as the integral of f of t dt. Okay, so this was t initial, t final. So that was impulse, and that impulse was equal to change in momentum. So we can say that similarly, the work W can be written as x initial, x final, f of x dx, and that's equal to change in kinetic energy. Okay, so there is that analogy between the impulse momentum theorem and the work energy theorem. Let's go to the next section and calculate work again. So this time we shall use work energy theorem. No, not work energy, but just dot products. So let's say that a mass m is pulled by a force F, let's say from a position x initial to a position x final, as shown below. Okay, so let's say we have something like this. This time we have a force F. This is at an angle theta. This position is x initial. The force F is still at an angle theta, and we can say this is x final. So we shall use the definition that we have of work. So this is from the previous frame above. I'm just referring to what we did above. So we had work equals integral of x initial, x final, f dx, like that. So we know that we can say that, let's see, we have, so the force in this case would be the force lying along the line. So we shall say, so we're just taking the f cosine theta out, where the f cosine theta is just the projection of f along this axis. So this is f subscript x, which is just f cosine theta, f subscript x, this is f cosine theta. So this is f subscript x dx, which is equal to f cosine theta dx, integrated from x initial to x final. So we shall say f cosine theta times x, x initial, x final. So the work can be written as f cosine theta x final minus x initial. So let's write it as work equals f cosine theta delta x. So we can write this in compact form by recognizing that f and delta x are both vectors. So we can use the product of two vectors to write the work as, say, work done is equal to f delta x cosine theta, which we can write as work equals f dotted with delta x. So the product of the two vectors f and delta x is called a dot product. So let's look at dot product of two vectors. For example, suppose we have two vectors a and b. Let's say this is vector a and that's vector b, and there's an angle theta between them. Then we can say that the projection of b onto a is this section here. This is equal to b cosine theta. So the projection of b onto a is the product ab cosine theta, and that's equal to a dot b. Okay, so the projection of the two vectors a onto b, of b onto a, is the product of the two, is equal to ab cosine theta. That's what the dot product means. If theta is equal to 0, then a and b are parallel, and we can say that if theta is equal to 180, then a and b are anti-parallel. So for example, if this is b and this is a and the angle is 180 degrees, then a dotted with b is equal to minus a times b. Okay, they are anti-parallel, and if they are parallel, then a dotted with b is equal to a times b. So when we are doing any work with force, we want the force and the displacement to be parallel to each other. So we can say that if theta is equal to 90 degrees, then a dotted with b is equal to 0. Okay, so this means that when force is perpendicular to direction of motion, then the force does no work. So when we do calculations with forces, we will calculate work for forces that are parallel or anti-parallel to the direction of motion. So parallel or anti-parallel to x, where x is the direction in which the object is moving. So let's take an example. So let's calculate the work done by the forces below. So we can say for the first one, let's say we have an object like this. A force F equals 10 Newton acting on this object, and taking it at delta x equals 5 meters, for example. We can take two forces, one that way, and we can say that this object is moving delta x equals 3 meters. We can have one like that where the force, this is 30 degrees, object is moving delta x equals 5 meters, and there's another force here, F equals 10 newtons. So we can calculate work by taking F dotted with delta x, and if they are at an angle of 0, then it's equal to F delta x. So this will be equal to 10 newtons times 5 meters, so that's equal to 50 Newton meters, which is equal to 50 joules, something like that. Okay, and you can do the same for the two other exercises there. So this is number 1. For number 2, you can try number 2 and 3. Its angle is 30 degrees. So number 2, what is the work done?
9 joules.
Okay, so we can say F times delta x. So this can be written as delta F times delta x. So you take the difference, so we have 8 minus 5 times 3. So this will be 9 joules. Okay, and then number 3, what is the work done? 160.
166.
And another person got what?
416.
We have 416. Okay, so let's take a look. So the work done would be equal to, so we have the force, we can have F dotted with x on the one hand for one of them, minus F dotted with x for the other one. So one of them is 50 cosine 30 times delta x minus 10 times delta x. Okay, so what is cosine 30? 0.866, I think.
Oh, wait.
0.86 times 50, 43.3.
Yeah.
Times 5 minus 10 times 5. Say that again. So 43.3 times 5 is what? It's about 216.
16.5.
Okay, thank you. Minus 50. So 216.5 minus 50. So that would be 166, right?
Yeah.
Joules. Okay, good. Questions on that? So I think we all got that. Very good. Okay, let's go to the next item there. So we can look at some of the work. Let's look at the work done by a variable force. Let's look at exercises involved in that. So let's look at examples of work by a variable force. We've seen one of those before. We looked at a spring force already, so we can say that, recall that we have done this with the spring force once. So for example, so we have from our definition that work is equal to the integral x initial to x final of f dx. With a spring, we had f equals minus kx, where x naught is equal to 0. So we are just saying that the reference point is where we have x naught equal to 0. So we shall say that the work done for a spring was equal to the integral x initial to x final of minus kx dx, which can be written as minus kx squared over 2 x initial x final. So we had minus k x final squared over 2 plus k x initial squared over 2. So try this exercise and let's see what you have. Any answers for work?
10.54.
Okay. So anyone getting a different result for the work? Okay, so we have 10.5 joules. Is everybody getting that? Okay, so work is equal to integral of f of x dx. We can say x initial, x final. So you can do work integral from 2 to 5. and then we shall have minus k x minus e raised to the power minus x times 2. So d is 2, so we can put in the 2 there. So let's put 2x dx, something like that. So when you integrate this, you have you can take the k out, so it's going to be minus k x squared over 2 from 2 to 5, and then you have plus okay, there's a negative sign there, so we shall have minus 1 over 2 e raised to the power minus 2x from 2 to 5, like that. Okay, so this is like writing minus k x squared over 2 to 5 minus half e raised to the power minus 2x 2 to 5. So minus k, and then you put 5 squared over 2 plus k, let's say 2 squared over 2, and then this is minus, and so the minus comes in. If you like, you can put this like that, and then we have half e raised to the power minus 10 minus half e raised to the power minus 4, something like that. Okay, and then there's a k, of course, so let's not forget the k. So let's say let k be equal to, say, 1. Okay, if you let k be 1, that makes it pretty simple. Then we shall just have in the first one minus 25 over 2 plus 4 over 2, and then we shall have e raised to the power minus 10 over 2 minus e raised to the power minus 4 over 2. Okay, so the only thing you need to do is calculate e raised to the power minus 10 and e raised to the power minus 4. Alright, so 21 minus 21 over 2, and then we have in here whatever that is. So approximately 10.5 joules. That's basically what it comes down to, minus 10.5.